And we are going to start. Still in lecture 00. We've learned nothing so far, but especially following this, the next two lectures are going to be kind of dry because we're going to do a lot of definitions. But at the same time, I really want you guys to kind of have an intuition of what we're doing in the background when I'm defining these definitions. And it'll help you to think about how you want to think about things. So sometimes I'm defining something. On one hand, it might seem weird and you're like, why would you define something like that? On the other hand, you're like, duh, isn't that obvious? But both of those reactions are actually the incorrect reaction. Once you realize in the background, my definitions have to fit on top of functions and how functions behave, then you can realize that it all makes sense. The things aren't defined arbitrarily. There is a purpose to why things are defined the way they are. And you really do, especially for those of you going on to even more advanced mathematics, you really want to get rid of this. Let's put it this way. Your intuition up to this point is really based on habit, right? You kind of assume certain things because of all the math you've been doing up to this point. That's the way things work. You'd assume things like multiplication is commutative. That's not true, right? So I don't want to, there's this inertia that you guys are going to have to fight. So there's sometimes I'm going to be defining things and you're like, why are you defining it this way? And it's because specifically your intuition will lie to you, starting now and on into the future. Okay, so things are, there's always a reason behind the definition. And because you've been playing with real numbers your whole lives, your intuition works on real numbers, but it will not always work on other things. And there are some things that make complete sense, and it's obviously when you're talking about real numbers and continuous functions, that make no sense otherwise. When I talk about commutativity, for example, it's actually a very weird thing. It's something that we think of as, oh yeah, sure, you can multiply in either direction. But in general, when we talk about all the different things that mathematicians study, finding something where commutativity works is actually very strange and very rare. So your intuition is going to lie to you a lot, so it's very important that we really take our time going through these definitions. And I think it's nice for you guys to kind of see the point of where things are. So when I define something, it's not like, what is going on? So in that end, we're going to just recall something we did last time. I'm going to discuss it a little more so you can get some more intuition based on that. Then I'm going to talk about something else that we're going to define, and that's the intuition behind it. Then we're going to go into definitions. This is what this is and why we call it this and whatnot. So last time I think we did technically some matrix multiplication, even though we don't know what that is yet. It was really defining a composition of functions. Let's remind ourselves what we did. So I said P was the function ax plus by, comma, cx plus dy. And I realized the fact that somehow we can use an alternate notation for this, in which case it was a, b, c, d. And I could think of, we did some things with this and we did some things with that, and realized that at the end they were equivalent answers, right? And so we had also q was ex plus fy, comma, gx plus hy. And this we could have represented as e, f, g, h. We also defined another function, r, that took ix plus jy, comma, kx plus ly, comma, mx plus ny. And we could have represented that by this machinery, ij, kl, and we saw some things in particular. We tried to, what are the two last operations? We're going to pick up towards the two last operations. We tried to compute P of R, right? Which I can write down as this, A, B, C, D. Put the R right beside it. I, J, K, L, and N. And we found that the answer was what? It was undefined, right? And it sort of, that made sense, at least I hope it made sense to you, when we thought of it in terms of functions and the x and the x, y, and z. The fact that this has an x, y, and z component, that only has an x, y component, it couldn't plug in a certain direction. However, we actually went the other way, Rp, which means this was I, j, k, l, m, n, and a, b, c, d, and we figured out that that actually did have a functional representation. In fact, we found that its functional representation would have been ai plus cj, bi plus dj, and ak plus cl, and we did here bk plus dl, and we found this was am plus cn, and this was bm plus dn. Right, and I kind of showed you guys that in two different ways. So we actually went through the tedious computation of actually plugging this into the other one, and we got an answer which was equivalent to this. It was this x plus that y, and then blah, blah, blah. And then I actually did this weird computation, this weird definition where I was like, okay, let's take this row and dot product it with that column for some reason, right? And we did that to create this row, and we did the second row creates the second row, and we did the third row creates the third row, and we ended up here, and they were kind of equivalent answers. Now I want to kind of look at this more closely, what we just did. Let's think of our R. If you had to describe P, imagine we're working with real numbers, and R. What set to what set are we going with? Let's think about we're in a real vector space, like Rn back in calc 1, 2, and 3. How do you describe P? What's the domain set? What's the range set? What does that mean? Yeah?
Isn't it R2?
R2.
So it started at R2, and then it went where?
R3.
R2.
It also went to R2. How do you know? Well, I didn't write it here, but what we said is P, we took P off a coordinate x, y, and its output was another thing with 2 coordinates, right? So it went from a 2-dimensional space to a 2-dimensional space. If I think of x, y, and blah, 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 all being real numbers and variables, I could describe this as moving a function going from R2 to R2. And I could write it as this way, if it's a linear function. Okay? What about R? This guy went from R2 to R3. Okay? Now what can you kind of map these numbers on top of this matrix? What do you kind of notice? Do you notice anything? Yeah?
The domain is the columns and the codomain is the rows.
The domain is the columns and the codomain is the rows. Notice in R, how many columns do we have? There are 2 columns. And how many rows did we have? There were 3 rows. We went from 2 to 3. This is not a coincidence. This is just how it has to be set up, right? So in other words, when we talk about this kind of object, the size, how many rows and columns it is, actually tells me about the function it's representing. If I count the number of columns, that is actually telling me what is the dimensions of the domain space, right? This is where I'm taking all the guys that plug into the function. This is the number of dimensions of the space they live in. Then it gives me the output, and that dimension is actually from the number of rows. Okay? Now think of that in terms of what we're doing here. And let's say for some reason I decided to measure a matrix like this by talking about in terms of its rows and columns, right? So let's say I described this guy then as a 2x2 function, and I can describe this guy as a 3x2 function. Okay? So what is this actually saying? And remember, our multiplication, what did it mean for us? Well, we were kind of doing a composition, right? But even though I didn't write it that way, we saw that it was equivalent to doing a composition. So basically, when you look at that, what is this saying? This is a function whose input comes from a 3-dimensional space, well, whose input comes from a 2-dimensional space, and whose output is a three-dimensional space. This one is talking about a function whose input is a two-dimensional space and whose output is a two-dimensional space. Okay? So now this here is 3 times 2, this here is 2 times 2. So now it makes, hopefully it will make sense. Let's actually just draw a picture here of what's going on. So here we have R2. Here we have R2. Here we have R3. Right? So in this second one, let me emphasize that I'm drawing this picture to represent this second situation. What I did was P did something. So P went from R2 to R2 based on how we set up this function. So that's what is our P function. And then our R function went from R2 to R3. So that's what R did. Now you can imagine for this guy, what would the pictures look like here? Well, first the R was doing something, and R went from R2 to R3. That's what R did. And so now, what happened was this part kind of broke, you might have noticed. Because what does P actually do? P, this couldn't work here, right? Because P took its input from R2, but this guy's outputting in R3. We couldn't make that connection. I couldn't take the output of this guy and plug it into the input of that guy, right? The dimensions just didn't match up, right? And so what we find here is because if we can think of this guy here as the input and this guy here as the output versus, well, input dimension and output dimension to be a little more clear. So this guy here would be the input dimension. This guy here would be the output dimension. So clearly we kind of come up with a rule for when this kind of operation would be defined. Here's a function that takes it from this input dimension to that output dimension, and clearly for this function to plug into that function, the output dimension of this must be the same as the input dimension of that. Otherwise, I can't plug the function in, right? So these two numbers have to be the same in order for this operation to be defined. The output of this must be the same as the input of that in terms of dimensions. But if you were to take the composition, what is the composition function? Do we remember what the composition function does?
3 by 2.
Yeah, on this picture, how would you describe the composition? If I were to draw R of P on this picture, what would it look like? Yeah?
It's R2 to R3.
It connects the first guy all the way to the second guy. Remember, a composition of functions was just a way to cut out the middleman, right? So the composition is going to start here and bring you all the way to the end. So now, if you look at this guy, what would the dimensions of this guy be? If we start at R2, that would be the dimensions of the input. We end in R3, that would be the dimensions of the output. And notice that here, we have that thing precisely happening. Right? And so, and what you can think of as the composition is the guy that goes all the way from here, all the way down here. Right? So this is what your R of P did. So your P did this, and then your R did this, and R of P just cuts out the middleman. Now in terms of the numbers that are represented here, you can come up with a rule that these two inner numbers have to be the same for the functions to connect and make sense connecting. The outer numbers actually tell you what the resulting function should look like, right? Because the outer numbers is the input of the very first set to the output of the very last set. And that would give you the size of that function that combines all those rules together. Yeah?
What if we had something like a 3 by 3 matrix or a 2 by 2 matrix, then that wouldn't work?
Well, let's examine that. I mean, we will go over this, but let A and B be two matrices, right? Now in the background, they're representing functions. And you said we had a 2 by 2? What did you say?
3 by 3 and a 2 by 2.
Like that?
Yeah.
So you see these inner numbers here, they don't connect. So we couldn't actually do that. What if here there was a 3 by 2? That's actually exactly the same, but if I put the 2 by 2 here and a 2 by 3 here, that's actually fine. That would actually work, right? We could get a new function that way. Now here's something else you should realize, right? So A times B really means A composed with B. That's what I really want to get across to you. And so these numbers have to line up. So let's take this example. You don't even know what the functions are, but it doesn't matter. And do it the other way. What if I do BA? Now what would the numbers look like?
Transpose.
This is going to be a 2 by 2, and this is going to be a 2 by 3. Now here, that was okay. But suddenly I switch the order, and that's not okay. The functions can't connect the other way. So in fact, not only is A times B not the same as B times A, but it's possible for this one to exist, and that doesn't even exist at all. It's that big of a gap. Right, so this idea of switching orders and everything is fine is a very wrong idea to bring into this class. It's not always going to be true. Yeah.
Are there any operations that you can always do with any set of sets?
Well, we'll get to that. So I'm going to define, again, because these guys represent functions. Remember, different functions have different behaviors. Some functions you can invert them, some functions you can't, some functions are one-to-one, and some functions are not. Right, so it will really depend on the kind of function we're looking at, and there you will be able to talk about what kind of function a particular thing like this represents based on the numbers. Right, but that comes later. This comes at the end when we're, well, more towards the middle of the class when we talk about all the different kinds of functions that we can have and what they would look like here. But it would really depend on the particular functions in mind. And there are some things that will only work on functions that are what we call square, like the number of input and output dimensions are the same, whereas it can't work on something like this. But again, it's all because in the background these are functions. So things that won't work with functions are not going to work with these. And the point of how we're setting up our definitions is to capture that kind of property. So you don't want to think of matrices as numbers. Your intuition will be all wrong. They are functions, and they go between certain dimensions, and the dimensions and everything have to line up. And so all the rules that we're going to be putting together for matrices, they will be put together with that goal in mind. So there are times when I'm going to have to tell you things like, oh yeah, you can add things in any order. And you're like, well, obviously, it's not obvious, right? But you can't multiply in any order, which might not be as obvious. But when you think of what the background is, it's going to make a difference. Okay? So that's kind of the idea I want to give to you, because a lot of times I'm going to just be putting definitions on the board, and it might seem completely stupidly obvious, or it might seem downright weird, but if you take a step back and look at that, this is just the user interface for something that's going on behind the scenes, and that will kind of hopefully give you some comfort. Well, that's my hope. Let's look at another kind of, we're still playing around here. But let's look at another kind of operation. Let's take this guy. Let's do the P again. So here's P. I called it AX plus BY, CX plus DY. And I know we could have represented it as A, B, C, D. Let's put another interpretation on this. Let's isolate the rows. Okay, so here's our first row, here's our second row. But here's how I want you to think about the rows. Think of each row as a vector, in the conventional sense of a vector. Okay, like back in R2, back in Calc 3 class. So basically, this is a vector where my x component is the A and my y component is B. This is a vector where my x component is the C and my y component is the D. Think of these as vectors in R2. Okay, so we can actually draw them. So let's say, just for example, I'm going to draw them as position vectors, and this is kind of how we, right? I'm just completely making this up, but I'll make a point at the end. So we're drawing them as position vectors. So my first vector, how would I draw that? Let's say they're all positive numbers, just to make things nice. I'll move over to the right by A, and then I'll move up by B, right? So that is actually B. That's a vector here. Right, so that's how we would draw it. Okay. Now let's say I'm going to draw this bigger so you can see what I'm going to do later. Let me draw this a little bit. Okay. This is basically the idea. That's that one, and I'm going to let this one be the other one. So this is my vector AB. I'm going to let this be my vector CD. You guys remember what the resultant vector from physics would be? We add those two vectors together. It's going to be a vector right through the middle, right? And it can actually create a parallelogram. Right? Okay, so that shouldn't be too strange so far. What would the coordinates of this guy be, based on what we know from R2? Yeah?
A plus C, B plus D.
A plus C, I add the x coordinates, and B plus D at the y coordinates. Okay, so here's the question. What is the area of this parallelogram? So let's actually try to figure this out because it's probably not obvious. We actually know about the area of a parallelogram. It's the base times perpendicular height, but to figure out the perpendicular height might kind of be annoying. So let's do this another way. I'm going to create a larger rectangle, and what I'm going to try to do is I'm going to find the area of that rectangle and subtract all the pieces that are not in the parallelogram. Okay, so let's actually do that to figure out the area of this guy. Okay, so what are we going to do here? So the area here is going to be, the area of the big square is going to be what? A plus C times B plus D, right? It's length times height. Okay, and let's subtract all the other parts. What would I subtract now? What about this triangle here? Right, that's a right triangle.
Half A times B.
Half base times height. So that's what? Half
A times B.
Okay, so I got rid of this triangle here. What about this rectangle here?
A plus C minus A times
That's A.
Yeah, so what's the length of this?
A plus C minus A.
A plus C minus A, so it's just C.
Yeah.
And the height is
B.
B. So it's just, what is that then?
C.
BC,
Yeah.
right? So that's that guy. What about this triangle here?
D.
D.
Times half C.
Okay, so we know half base times height,
That's
and the height is
the height is
D, because we know that to get to this level was B. The total height is B plus D, so the height here is D, right? So it's 1/2 CD, or DC, or whatever. Okay, so that gets rid of this guy. What about this guy here?
A. That's the height.
What's the height?
A, like,
This length here is what?
yes. A.
That's A?
A. Yeah.
So it's minus 1/2 A What's this?
B. B.
So it's this, or this rectangle here.
C. A times B.
Hmm?
A times B.
C times
C
C
times-
C times B.
It's C times B. So that's this guy. And one more, what's this guy here?
1/2 DC.
Hopefully we did that correct. Let's actually simplify. So this multiplies out, I get AB, right, plus AD, plus BC plus CD, minus, these two can kind of combine, right? So I have just minus AB, minus, so that kills those guys. Here I have minus 2BC, that's those guys. Here I have minus DC, that's those guys. So what do I have now? Well, I have AB minus AB. I have CD minus CD. So I'm left with AD
Minus BC.
minus
BC.
plus BC minus 2BC is minus BC. So the area of this parallelogram is given by that expression, AD minus BC. Now here's something that's totally weird. That's this times this minus this times that. So for A, B, C, D, the expression AD minus BC gives the area of the parallelogram with sides A, B, and C, D. Now it turns out that's not exactly a correct statement because I could have wrote these vectors, if my A, B was on top of the B, C, I would have gotten the negative of this answer. So we can kind of change this a little bit as the signed area, because it might give me a negative answer depending on the orientation of the vectors. But it turns out that for a 2x2 function, this expression is particularly important. And of course, us all being calculus students at one point, we know that something that finds the area of something it can be pretty important and have many applications besides just area, right? Think of the integral. The integral was just finding an area, but it has so many applications. Turns out that this expression for this function will also have many applications that we'll talk about, and we actually call it a name. It's called the determinant. Of the A, B, C, D, right? So a determinant is a function that goes from the set of some matrices that you're talking about to another set, which is the set of real numbers, and it gives you a number as an output. That number, what that number represents, is the area of the parallelogram spanned by the vectors in the matrix. Can anyone think of a higher dimensional analog of this? Who here remembers their Calc 3 a lot? Yeah?
For a 3x3, I think it would be wouldn't it be an alternating sum?
Almost. Back in Calc 3, when you had to do something like,
The cross product.
when you had in 3 space, you had a parallelogram where there was one vector and this vector and that vector, and you sort of created something like this.
Yes.
You remember what that was? They call this a parallelepiped, I think.
There we go.
Was it cross product?
I don't remember.
Yeah.
Anyway, so when they asked you to find the volume of the parallelepiped, do you remember what they asked you to find? It was the magnitude of something they call the scalar triple product, which you just put the vectors here, B3, B1, B2, B3, and C1, C2, C3, right?
Yeah.
They were actually asking you to find a determinant. So it turns out you can think of a determinant as something even more general. If you have an n by n matrix, and if you think of, because all my vectors have to live in the same space, it would have to be a matrix that's square, right? It gives us the n-dimensional volume, right? So of course, since we're only in 2 dimensions here, it gives me a 2-dimensional volume, which is area. That's what area is, a 2-dimensional volume. And so this expression is important in relation to the vectors that appear in this function. Okay? So there's going to come a point where I'm going to define for you what a determinant is. I'm going to give you this random definition. You're going to like, what the hell is that about? And this is kind of the background. I'm going to give you a formula that will compute the area of the parallelogram of the vectors, if that's spanned by the vectors. So the application in this was the scalar triple product, is the application you would have seen in Calc 3, where we had 3 by 3 vectors. So there will come a point where I'm going to just tell you, oh, the determinant of a 2 by 2 is this. You just multiply this by this minus that by that. It's not a random definition. It was really just a definition to capture this manipulation here. Okay? And you can do this in general. So basically what they did was they did this in general for n dimensions. They figured out a pattern, and then they came up with a definition that outputs that pattern. And that was called the determinant. With that being said, let's actually start making things precise. So what I do want you to take from this is clearly, oh, let's actually do something else. So based on the composition rule that I gave you, can you tell me what is this? If I take A, B, C, D, and I compose it with X, Y.
AX plus BY.
The result would be AX plus BY, right? We did the dot product of the first row times the first column, and we exhausted that. And so this is actually CX plus DY. And what was that? That was our function P. In other words, I could say that P of xy is equal to A, B, C, D times this vector xy. In other words, if I call this guy a capital letter A, and call this guy a generic vector letter that would represent my coordinate system, I could write P as this kind of expression. So this object here is what we will call a matrix. And as you can see, a matrix can represent a function. In fact, I can write any linear function as a matrix times a vector that's describing the space that I'm working in. And so, did any of you take 08? One person took 08? Oh, wow. Okay. So in other words, to study this function, we can study the matrices, right? Because manipulating this matrix is the same as manipulating this, and this is kind of equivalent to that. That's one thing. And the space where these entries live here, in this case that we've been doing, is actually like Rn. Like we were looking at the space R2 and R3 and so on. And so we can talk about where the numbers in here come from. So these guys are all representing real numbers. That's what's populating this guy, right? It doesn't have to be what's populating this guy. And this guy here is a member of R2, right? So in other words, we can talk about functions. This I can think of as a function that lives in this space, okay? And therefore, studying this is the same as studying a function that lives on this space. Now, the point I'm going to try to make is probably a point that you had to make. It's something that would hit home for more if you actually did 308. In 308, you started doing set theory. And you actually proved that there are more real numbers than the natural numbers. You guys did that, right? And how did you actually come to figure that out? Do you guys remember how you proved that? Do you remember what you did? You actually figured that out using a function, right? So first you figure out the idea, because clearly there are an infinite number of integers and there's an infinite number of real numbers, right? So you can't literally like count them all and say that, oh yeah, they have the same. You can't actually count them. So you have to come up with a very ingenious way of counting, right? So let's say I have one group of objects and I have another group of objects and I want to figure out, are they the same size, right? One way is to literally count them all, but that's not always very efficient. In the case of if this group of objects was the integers and that was the real numbers, that would not work. But there's another way, right? Let's say I have a bunch of you guys just standing over there and I have a bunch of chairs in the classroom and I want to know, do I have a seat for everyone in the classroom, right? Is it the same number of chairs as there are people? Instead of wasting the time like counting the number of people and counting the number of chairs, what could I do? Just ask you all to sit down. In other words, I can make an assignment. I can assign one individual to each chair. That's creating a function, you know? So I have a function that assigns people to chairs. And at the end of the day, what I look at is, one, I want my function to be one-to-one. I only want one person in each chair. And also, I want to check if my function is onto. Are all the chairs filled at the end of the day? And I can actually make a conclusion at that. If I have chairs left over after everyone is seated, then there were more chairs than there were people, right? If I have all the chairs filled and people still standing, there are more people than chairs. If I have all the people sitting and there are no extra chairs, then I knew there were the same number of people as there are chairs, right? So another way of, if this had 3 objects and that had 3 objects, one way I could tell that they are the same size is just by assigning each thing here to there in such a way that it's one-to-one and onto. And if it's possible for it to be one-to-one and onto, it means that the number of things in here is exactly the same as the number of things in there. The point of this being is that I can tell things about this group by using a function. The point of why we care about studying functions in the first place is not just for the functions themselves, but they can actually tell us about the group of things that I put the function on. I can use a function to determine how many things are in this group. Right? So let's say this is a set that I'm very familiar with. I know all the information about this set. But this is a very weird set, right? It's something I've never encountered before, and I want to study that set. So I want to know how many things are in it. Does it have operations on it that behave like the operations in this set? So what I can do is I can create a function from one to the other, and that can tell me how many things are in it. And then certain properties of the functions can tell me if elements over here behave the same as elements over there. Right? So in that way, let's say this was R2 and that was R3, and I can think, do those things have the same number of elements? And would the elements in here behave exactly the same way as the elements in here? I can figure that all out by using a function from one set to the other set. Right? So the point of why we actually want to study these functions is to actually help us to know about the groups in which the domain and the range live. We can actually tell a lot about the groups, the sets that we're looking at, by looking at the functions. So in other words, when I'm looking at matrices, I'm looking at the functions that connect 2 sets. And by looking at that function, I'd be able to talk about the 2 sets. Especially if I create a function from one set that I know everything about to another set that I don't know everything about, I can sort of figure out things about this set because of the things I know about that set. So this is a way that mathematicians, if they come across a new object and they kind of poke around to see what is its properties, usually what they do is they take something that they know all the properties, create a function that has certain properties to go to this other thing that they don't know about, but based on how the function behaves, they can tell you how this set behaves, right? So to that end, this is kind of why linear algebra is useful, because sometimes we can talk about things that we are not familiar with in terms of things that we are familiar with. And a very efficient way to do that is with a set. and a function on that set. And a very efficient way to talk about these functions is by using these rectangular arrays of numbers that we call matrices. And so that ends lecture 00. So starting in our next class, I'm actually going to talk about these things here that are called matrices. I'm going to tell you how they work, how we name them, operations that we can do with them, and just how all the properties that they have in general, because that will help us to study the sets that we're going to want to be connecting. For the most part in this set, we are going to be looking at R2 and R3, but again, I don't want you to be married to the set that we're looking at. I want you to think of everything in abstract and general, and just think of things in terms of functions and domains and ranges and making connections, but don't necessarily be married to all the intuition that you had from previous classes. So we'll end there. No, we actually have a half an hour left. Okay, so I will go right into definitions then. And none of you even told me. You guys are going to make me let you go a half an hour. It's been a long week. It's been a long week. I don't even remember. Like I'm teaching 6 classes this semester, and like 4 or 5 of them end on the 15-minute after the hour. Like 4 of them end. So I'm just used to, oh, it's 15 minutes. Let's get out of here. That's not true. We go to 45. Okay, so hopefully that gives you an appreciation for some of the things we will be studying. And so you can see why things have to work out a certain way. Because we're really talking about functions when we're manipulating these things. And why we care about the functions is because they can tell us about the things that we're connecting with the functions. So now we're going to jump to 1.3. I'm kind of changing the order a bit, so we are going to do 1.1 and 1.2, but I think it's more efficient to do that after 1.3, because 1.3 has a lot of useful definitions. I think how the book is set up is in 1.2 and 1.3 kind of did a thing like I did, where it played around with stuff and then it summarized it in 1.3, but it didn't summarize it in a way I liked. So I think it's nicer to start at 1.3. I'll give you all the definitions and we'll go back to 1.1 and 1.2 and figure them out. So I think the title of this is Matrices, and Matrix Operations. And we're not assuming anything here. I'm assuming you guys don't know anything, so we're going to start from the very basics. Definition. A matrix is a rectangular array of numbers or objects. Right, so that's how a textbook might define them, but you guys know that in the background, they represent functions. Right, but at this point, the textbook will kind of introduce things in a very abstract way. This is a rectangular array of numbers. Here's the things, blah, 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 blah. But really, the reason why things work out the way is because in the background, they're representing functions. Okay. The numbers, objects in the matrix. Matrices is the plural of matrix, by the way. Are called entries. Example. 1, 2, 3, 4 is a matrix with entries 1, 2, 3, and 4. So it's a rectangular array of numbers. Each element in that rectangular array is called an entry. Another definition. let's talk about where I want to talk about this. It's not very definition. We can name our matrix and each entry. Usually uppercase letters. For the matrix and corresponding lowercase letters with subscripts for the entries. Example. I can say A is a matrix. An entry is A, little a, where I put an I and a J here, where I represents the row of that entry. This guy tells you the row that that entry is in, and this guy tells you the column that that entry is in. So another example, if my A is 1, 2, 3, 4, then I can talk about A11 is 1. I can say A12 is 2. I can say A21 is 3. And I can say A22 is 4. Right, so that's standard notation. If I give the name of the matrix in uppercase, I put the lowercase with the subscript to describe the entry. So I can say the entry in the first row and first column is this guy, that's a 1. The entry in the first row, second column is this guy. The entry in the second row, first column is this guy. The entry in the second row, second column is that guy. So we can name matrices and their entries. We can also talk about the size or dimension of the matrix. If A has n rows and n columns, it is called an n by m matrix. This is called n by m. Example. 1, 2, 3, 4 is a 2 by 2 matrix. 1, 2, 3, 4, 5, 6 is a 3 by 2 matrix. And in this case, I could write big A, and I can emphasize that it's a 2 by 2 by writing a little subscript 2 by 2. Here I can write this as B, where B is going to be a 3 by 2. So I can write that. So we determine the size of a matrix by listing it row and row by column. Right? So that's normally just a definition they throw out, but we can kind of see why it was important to do the row first and then the column, right? Because it's easy to see if these two functions will play well together when you line them up right beside each other. Right? So it wasn't just an arbitrary decision to list the row first and the column second. Nothing is arbitrary. There's a reason for everything. Okay. So matrices with n rows and m columns is called an n by m matrix. What's that I want to tell you? I don't know if I have to tell you what that is. So columns obviously are talking about vertical things, rows are talking about horizontal things. Rows are numbered from top to bottom. Starting at 1. Columns are numbered. Left to right. Starting at 1. Okay, so I have 1, 2, 3, 4. This would mean row 1, which I might call R1, is just going to be 1, 2. Whereas row 2, which I might call R2, is going to be 3, 4. I call column 1. That's going to be 1, 3. And column 2 is going to be 2, 4.
What is it, pound sign?
Number. It was short for number. Numbered. I just got
But it's,
these.
you're using R for plural, numbers, okay, number.
Definition. And M by, well, usually N by N, but it doesn't matter really. An N by N matrix is called a square matrix. Right? That's important to know because there are a lot of theorems and rules I will have that will only work for square matrices and they don't work for other matrices. And those rules would make sense when you realize that what that means is the input dimension and the output dimension are the same. Right, and so that will kind of tell you why some rules will work or some won't, while others will. I might call it, so if you have a 1 by n matrix, we might call that something. That means it has 1 row and n columns. That's called a row vector. The word vector we'll be using a lot more general in the future. There's an m by 1 matrix. That means it has 1 column. This we call a column vector. Let's talk about equality. Two matrices are equal if they have the same size and the corresponding entries are equal. So they have to look exactly the same to be equal. So you can have something like 1, 2, 3, 4 clearly should be equal to 1, 2, 3, 4. Or let's just see an example. Let's say in one matrix you know everything about, but through some way you can figure out some other matrix where you might have an unknown, something like 1, x plus 1, 3, 4. This would mean, of course, that your x value has to be 1 in order for the equality to be maintained, because each corresponding entry must be the same. it's addition. Let's do subtraction at the same time. Although, technically, we should define scalar multiplication. Talk about subtraction, I think it's okay here. So, we can add, subtract matrices only if they have the same size. And I can also talk about a definition here. If A n by m and B n by m are matrices, then the matrix A plus B is also going to be an n by n matrix, and it's going to be the definition where you're going to take the Aij's and you're going to add them to all the Bij's. All right, so you add the corresponding entries. That would be the definition. So 1, 2, 3, 4, plus squares plus or minus. You just add the corresponding entries. They have to be the same size. And again, we know this because we're adding things in functions. We have to add, we can't add a 2-dimensional vector to a 3-dimensional vector. So they have to have the same size. So this would just be 1 plus 4, 2 plus 0, 3 plus or minus 1, and 4 plus 2, 5, 2, 2, 6. If they don't have the same size, the sum is undefined. So I believe on the last quiz I gave you that sort of situation where I told you 3 matrices and I asked you to add a bunch of them. Not all of them could be added. The answer would have been undefined. You could only add them if they were exactly the same size, same number of rows and columns. Because that means your input dimensions and output dimensions are the same. Scalar multiplication. We can multiply matrices by scalars. If A is an n by m matrix, then Ka is just the matrix where I take K times all the Aij's. So I can just multiply each entry, i.e. multiply each entry by the scalar K. In this class, our scalars will always be real numbers, but in general, a scalar is just an element of a field. You probably don't have to worry about what a field is for now. That's kind of something you'll study in abstract algebra. But essentially, a field is where your intuition from real numbers actually works out. It's just any set that behaves like the real numbers. So you can have division and all that stuff, which again, is another weird thing. Just like how I said being commutative is weird, being able to divide is actually pretty weird as well. And sets where you can divide and you have commutativity and associativity of multiplication and addition, those are called fields. Yes?
Weren't they also the definition of a linear transformation? Like something was a linear transformation if it had these properties.
Right?
So are all
No, that wasn't.
That wasn't, okay.
It wasn't a definition. You'll notice in the list of 10 things that I told you define a vector field, there was no division. Right? Like I never just defined for you a multiplicative inverse. I defined an additive inverse. It's very different from a multiplicative inverse. Right, so a field would have multiplicative inverses. Vector fields don't. Right, in fact, in a matrix, there is no such equivalent. Right, in fact, not all matrices have multiplicative inverses. Some do. They have to be all square matrices, by the way. So if you're a non-square matrix, you all automatically don't have a multiplicative inverse. And so for matrices, division is weird. It's not really division, and it only works sometimes. It's not like with real numbers. As long as you're not dividing by 0, you can literally divide anyone by anyone else. In matrices, that's not the case. Division doesn't really exist, and you can only even do something similar to that in a very small amount of cases. But we can multiply any matrix by a number, and that's fine. It's just multiplying each.
You can have scalar division, but you can't have matrix division.
Well, scalar division and scalar multiplication is
Yeah.
essentially the same thing. You multiply by 1 over k versus k. You would think of it as the same thing. So example, again, if my a is 1, 2, 3, 4, then I can take minus 2a to be minus 2, minus 4, minus 6, minus 8. Right, just multiply each individual by that. And so that was also something that you could have used on the last quiz. That was in the bonus section. Zero matrices. Plus and times is defined in the usual way. Zero matrix is the matrix so for example, A equals 0 or A equals 0, 0 or A equals 0, 0, 0, 0, 0, 0, 0, 0, 0 are zero matrices. With addition and subtraction. Defined as above. So if I define addition and subtraction in this way, a zero matrix will just be a matrix with all entries 0. And yes, I'm implying there are other ways to define addition and multiplication. There are cases in which we don't want to define addition this way, and so our zero matrix would be something else. I could tell you that definition, but I think I'll just jump into matrix multiplication here. Matrix multiplication. So this is going to be the first weird definition. Everything it seems like, oh yeah, you add two matrices, you add the corresponding entries. You subtract two matrices, you subtract the corresponding entries. So if you multiply two matrices, you should multiply the corresponding entries, right? No. That's not the case. That's not how you multiply matrices. Okay. And why? Because it's representing composition. They never say that at this point in the textbook, but that's why. This represents a composition of functions. It's not thinking of multiplication in the conventional way. So let A, B be matrices, the product A, B is only defined if, and we actually made this definition up, we kind of figured this out. What would have to happen for that to work?
The output, the output of the first one and the input of the second must be the same.
Right, but let's make it simpler in terms of the numbers. If the number of columns of A equals the number of rows of B. Right? That is the only time it will be defined. This multiplication will not make sense in any other time, and that's because the number of rows is giving you the output of B, and the number of columns is giving you the input of A. So the number of output dimensions from this guy has to be equal to the number of input dimensions from that guy, which means the number of rows here must be equal to the number of columns there, and that is the only way this product will be defined because it's modeling composition. And if this is the case, then AB is equal to the matrix Cij, where, let me give dimensions here. You can probably write it in a subscript, but I'm going to rewrite it. So let A be an n by m, and B be an m by p matrix. You can just write this little subscript in these B matrices. And then this guy has to be equal to that guy. This sentence tells you that's not an accident. This has to be the case. Then A times B will be a matrix, and the size of that matrix will be an n by p. Where Cij, the position, the entry in the ijth position is going to be equal to the ith row of A dot product with the jth row of B. So addition and subtraction kind of defined in the way you'd expect. Multiplication is defined in this weird way. First of all, these numbers have to match up in a certain way, and then the definition is to take a dot product of rows and columns. And why? Because it's composition. That's how the composition is going to work. And because the rows are the output dimensions and the columns are the input dimensions. And so you have to connect them in a certain way. And so that's why matrix multiplication has this weird definition. It is something that we kind of have to get used to, so I should probably do a bunch of examples.
You mean column, the J column?
A column here, yes. By the way, this means matrix multiplication is not commutative. That means the order in which you multiply matrices matter, i.e., AB is not the same as BA in general. They can have different sizes It's even possible for one to exist while the other doesn't. Matrix multiplication is going to be a very common thing we're going to be doing, so you should know how to do this relatively quickly. So I think I want to actually stay here while I do a bunch of examples, but we're now actually out of time. So we'll stop there. But yeah, now things took a turn for the worse. And this will happen throughout the semester. There are some things where it's like, oh yeah, that's obvious, and then I throw this definition out there, like, well, why? Which is kind of why I spend the last 2 classes kind of playing around with stuff. So we'll stop there. I'll see you guys on Tuesday. And we'll have another quiz on what we talked about today. And I'll probably throw in some multiplication in there as well. Hold on, let me turn this off.